Welcome to EDU World Space.
For part A of this problem, we are assuming that ball A strikes balls C and B simultaneously. So, during the impact, the contact impulses make 30-degree angles with a velocity v0. So, here we have ball A moving with initial momentum m v0. It strikes balls B and C simultaneously. After the collision, ball A moves in the same direction with momentum m va. Ball B moves at an angle of 30 degrees and momentum m vb, and similarly ball C moves at an angle of 30 degrees below the x-axis with momentum m vc. Remember, the mass of the three balls is the same. So thus from here we can see that vb is equal to the magnitude of vb times, so we resolve these into its components, x and y components. The cosine of 30 degrees times I plus the sine of 30 degrees j, and the final velocity of c is equal to vc, which we wish to calculate the speed of c, multiplied by the cosine of 30 degrees I minus sine of 30 degrees j. And by symmetry, va, the final velocity of ball A, is equal to its speed in the direction of I. Now we'll apply the conservation of momentum to give us a relationship between these velocities. So the conservation of momentum tells us that the initial momentum before the collision is mv0 is equal to the momentum after the collision, which is mva plus mvb plus mvc. So the momentum after is the contribution of the momenta of each of these balls. So we break these down into the y component and the x component. So the y component of the momenta, 0 initially, and 0 again for ball A, since it only moves in the x direction, plus mvb sine 30 degrees minus mvc, again sine of 30 degrees. Now we'll do the same for the x components. So essentially we're transforming the vector equation into two scalar equations. So mv0 is equal to mva, where v0 and va are the initial and final speeds of A respectively, plus mvb cosine of 30 degrees minus or plus mvc cosine of 30 degrees. So we can rearrange this and divide both sides by m and see that vb plus vc is equal to v0 minus va over the cosine of 30 degrees. So this is equal to 2 over the square root of 3 into v0 minus va. So we have that VB, we'll write VB in terms of VC and VA. So VB is equal to VC by symmetry is equal to a half of the term above, V naught minus VA over square root of 3. So the x components of VB and VC are the same after the collision. So that was the conservation of momentum. Now we'll use the conservation of energy. So the conservation of energy tells us that the initial energy, which is the kinetic energy due to ball A, is a half mv naught squared. The energy after the collision is a half mva squared, the kinetic energy of ball A, plus the kinetic energy of ball B, half mvb squared, plus the kinetic energy of ball C, a half mvc squared. And so rearranging this, we see that v naught squared, if we divide both sides by a half m, is equal to va squared plus, and now we'll rewrite vb and vc in terms of v naught and va. So that's plus 2 over 3 into v naught minus va all squared. So what we can see is that v naught squared minus va squared is equal to 2 over 3 into v naught minus va all squared. And so we're essentially left with only one unknown. If we assume that v naught is known in any given circumstance, and we rearrange this equation, we can see that if we do a bit more simplifying, we get 1/3 times v naught is equal to minus 5 over 3 va. And therefore, va is equal to minus 1 over 5 v naught. Similarly, once we have va, we can find the velocity or the speed of b and the speed of c, which are equal after the collision, and that's 6 over 5 times the square root of 3 times v naught, which is the same as 2 root 3 over 5 v naught. So va is essentially 0.2 v naught, and that's to the left. vb and vc are equal to 0.693 times v naught, where vb moves in the direction of 30 degrees above the x-axis, and vc moves off in a direction, or c moves off in a direction 30 degrees below the x-axis. Now for part B, we'll assume that A strikes B before it strikes C. So we'll break this up into two parts. And the first part is the first impact, that is A striking ball B. So in this collision, during the impact, the contact impulse makes a 30-degree angle with velocity v naught. So we have ball A moving with initial momentum m v naught. It then strikes ball B, and we can ignore ball C initially. And after this collision, ball A then moves in the direction of ball C with momentum m VA prime. Ball B moves off to the angle of 30 degrees with the positive x-axis with momentum m VB prime. Or actually, we'll just call this MVB. And remember, ball C is not part of this event, so it hasn't been impacted as yet. So from here, we can write down our velocity components, velocities in terms of I and J components. So VB is equal to VB into the cosine of 30 degrees in the I direction plus the sine of 30 degrees in the J direction. Then we can apply the conservation of momentum. Remember, we are only applying the conservation of momentum to ball A and ball B. Ball A has initial momentum mv0, and the momentum of ball B is 0 since it's at rest. The final momentum is mv A prime plus mvb, the momentum of ball A as it moves towards ball C, and the momentum of ball B as it moves off with momentum mvb. Now we'll break this again into its x and y components. So the y component initially is 0, and afterwards the y component is m va prime in the y component plus m vb sine of 30 degrees. And the y component of va prime is equal to minus vb sine of 30 degrees. So it's the opposite of the y component for ball B, since it moves in the opposite direction. The x component of this equation, v naught, is equal to, or mv naught is equal to m into v a prime in its x component plus m vb times the cosine of 30 degrees. And again, we can write down the x component of va prime. So va prime's x component is simply v naught minus the x component of the velocity for ball B, vb cos 30 degrees. So we've written the a prime components in terms of the components of vb and the initial velocity v naught. This is the x component, not the y component. va prime x component. Now that we have both these components, we'll apply the conservation of energy. So we've applied the conservation of momentum. We know that energy is also conserved. More specifically, in this case, kinetic energy. The initial kinetic energy of the system is that due to ball A, a half mv naught squared. The final kinetic energy is the kinetic energy due to ball A and ball B as they move off. That's a half m v a prime x component squared plus the energy a half v mv a prime y component squared plus a half mvb squared. So we've just broken up the v prime components, the v prime for a, into its x and y components. And we can rewrite this equation. If we do a bit of mathematics, we get this is a half m into v naught squared minus 2 v naught. Remember, we're just using our expressions for v naught from above. 2 v naught vb plus vb squared cos squared of 30 degrees plus vb squared sine squared of 30 degrees plus vb squared. And so from here, we can see that we can write vb as being equal to v naught cosine of 30 degrees. So that's the square root of 3 over 2 times v naught. And the velocity at which a moves off, va prime, has x component v naught sine squared of 30 degrees, which is 1 over 4 v naught. Finally, the y component of the velocity of a as it strikes, after it strikes ball B, is minus v naught, and it needs to be negative since it moves down towards ball C, cos 30 degrees times sine 30 degrees, and this is equal to minus the square root of 3 over 4 times initial velocity or initial speed v naught. So this is what we have after the first impact, after ball A strikes ball B. Now finally, for the second impact, ball A, after having struck ball B, now strikes ball C. So the second impact, A strikes C. During the impact, the contact impulse makes a 30-degree angle with velocity v naught. So ball A now moving in this direction with initial speed m, va prime strikes ball C. And remember, ball B is not involved in this impact. And after the collision, ball A moves off in another direction with final velocity, with final momentum m va, and hence final speed va. Ball B moves off with momentum m. Ball C, moves off with mvc in the following direction. So it moves off at an angle of 30 degrees below the horizontal. And again, ball C is not part of this impact. So thus, again, we can write Vc in this case in terms of its components. So that's Vc times the cosine of 30 degrees in the I direction minus the sine of 30 degrees in the j direction. Again, we'll apply the conservation of momentum. So the conservation of momentum tells us that the initial momentum due to ball A, mva prime, is equal to the final momentum of ball A, mva, plus the momentum of ball C, mvc. Now again, we'll break these into its x and y components. So the x component, and we'll divide both sides by m, we get that VA's x component is equal to the x component of VA prime, the initial velocity of ball A, minus VC cos of 30 degrees. And this is equal to 1 over 4 V naught minus VC cos of 30 degrees. We've already calculated VA prime. Then we do the same for the y components. If we do the same for the y component, we get that VA has y component of minus the square root of 3 over 4 V naught. Again, we get this from the first impact, our calculations from the first impact, times V naught plus VC times the sine of 30 degrees. So now we have our x and y components of the final velocity of A. And again, we'll turn to the conservation of energy. Conservation of energy tells us that the initial energy, a half, and we'll break it into its components, VA prime, the x component squared, plus the y component of A, half m VA prime y squared, is equal to the final velocities, the final energies, a half m VA in the x direction squared, plus a half m VA in the y direction squared, plus a half m VC squared. So a very long expression from the conservation of energy. So now we'll substitute our values for VA prime, the x and y components for the VA prime, in terms of V naught. And we also have expressions for VA. So what we end up with is a half m into 1 over 16 V naught squared plus 3 over 16 V naught squared is equal to a half m, and we can actually divide both sides by a half m to get rid of it, into 1 over 4 V naught minus Vc. So all we're doing now is just substituting expressions, times the cosine of 30 degrees plus, and that's all squared, plus minus the root of 3 over 4 times V naught plus Vc sine of 30 degrees, again all squared, plus Vc squared. And so if we do more mathematics, we end up with Vc in terms of V naught. So essentially, if we know V naught, we have one equation with one unknown. So doing the mathematics, we get that Vc is equal to V naught into 1 over 4 times the cosine of 30 degrees plus the square root of 3 over 4 times the sine of 30 degrees, and this is equal to the square root of 3 over 4 times V naught. Similarly, we can solve for the x component of VA, and VA's x component is equal to 1 over 4 v naught minus the square root of 3 over 4 v naught times the cosine of 30 degrees, and this is minus 1 over 8 v naught. The y component of VA, the final velocity of A after it has struck both balls, is minus the square root of 3 over 4 v naught plus the square root of 3 over 4 v naught sine 30 degrees, and hence we get the final y component of A's velocity to be minus square root 3 over 8 v naught. So now we have our speeds for A, B, and C with respect to the initial velocity v naught at which the ball A strikes the other two balls. So VA is simplified as 0.250 multiplied by the initial speed v naught, and this final velocity has an angle of 60 degrees below the negative x-axis. B has a final velocity of 0.866 times the magnitude of v naught, and it moves off at an angle of 30 degrees from the positive x-axis. Finally, Vc is equal to 0.433 times the magnitude of v naught, and this moves off at an angle of 30 degrees below the positive x-axis.